beyond standard model physics. But of course, although there can be anything, there are certain motivations for looking for something more specific, and one of these motivations is the observed dark matter in the universe. And I will tell you why this is a possibility at LHC. I am not going to talk about the theory of dark matter in general, except for the fact that I will remind you some concrete numbers. That is, the number of satellite-based experiments have measured the total energy consumption, or rather the total energy distribution of the universe, and it has been established that ordinary matter means, matter like us, which mainly interacts via electromagnetically. Although our body is neutral, you know that whatever interaction we do are basically electromagnetic interaction. Two neutral atoms or two neutral molecules interact by electromagnetic interaction, something like van der Waals force. And when we interact, although millions and billions of atoms are interacting, it is basically something like electromagnetic interaction. And this is what happens. So that is only about 4.9%. This is about 26.8%. This is called dark matter. Dark matter means this is not interacting electromagnetically, only gravitational and weak interaction. These two are the only allowed interactions. By definition, that is dark matter. And finally, I will not talk about it at all. In fact, this is not a subject of, it is not clear whether it is a subject of particle physics. This is dark energy. So we will focus on this dark matter, and just to show you the fact that they do not interact electromagnetically, this is probably a very nice and informative picture. You see, this is what is called the collision in the bullet cluster of galaxies. Now this is a picture which is after the collision. Roughly speaking, this is one of the colliding galaxies, and this is another colliding thing. These colors are artists' imagination, but what is red is matter which can be detected by X-ray emission. Now this is basically the gas which was contained in the two galaxies. Now what is important is that you can easily see that they are distorted. Moreover, this is the situation after the collision. So they are behind the dark matter which is represented by the green. Now how do I know that there is dark matter over here? This is by the so-called gravitational lensing. Again, this is basically there are background galaxies, and their light when passing through the dark matter, light bends. If it passes through a strong matter field, it bends, and this is how they draw the distribution. But what this tells you basically is that this dark matter can only have weak and electromagnetic interaction. That is why even after the collision they have retained their shape. You see clearly this follows the galaxy shape after the collision. So does this one, but not the electromagnetical interactive thing, because they are interacting more intensely and they are held back in the collision region, whereas the two galaxies have passed through the collision region and they are now well separated. Therefore, this picture actually is one of the direct evidence which indicates that dark matter must be weakly or gravitation interacting. It can have no other interaction. So such a dark matter is called the WIMP dark matter, that is weakly interacting massive particle. It must be massive, otherwise there will be no gravitational lensing. So it has to be massive and has to be weakly interacting. Now this is all very nice, but what it has to do with the LHC? These guys are sitting over there in a galaxy billions and billions of light years away. So what it has to do with the large hadron collider? The answer lies here, that if they are produced in the LHC, they will carry missing transverse energy. Symbolically this is so what is missing transverse energy? What is transverse energy to begin with? Well, as you know, energy of a particle is what? So according to the Einstein formula, total energy is just mass of the particle squared plus total momentum. But if you break the total momentum as the longitudinal momentum and the transverse momentum, for example, you can take this direction, which is the direction of motion of the particle, call it z-axis, then its momentum in the z direction is the longitudinal momentum. And in the xy plane, which is transverse to the z-axis, there are two other components of momentum, px and py, that is pictorially added to give you the transverse momentum. So I would like this very good. This is well-known undergraduate definition of energy. But now let us say that suppose we make a new definition and forget about the longitudinal. That is, I make a new definition, Et, and I say that this is simply, this is a definition, nothing more. Now why do I make this? Why do I make this? Well, let us look into the collision in a collider. That is, two beams, they are hitting in this case. Now remember, this has to be in a beam pipe. I saw you those pictures in the morning that there were two pipes almost side by side and then they intersect at different points. So the protons are flowing through those two pipes. The trouble with the pipe is, as soon as you have a pipe here, you cannot put a detector inside the pipe because that will interfere with the beam. The beam will be destroyed. Therefore, you cannot measure. So because of the beam pipe, Because what is happening in the beam pipe, how much energy flew through the beam pipe you know. That was the energy carried by the two beams. But after the collision, obviously something will flow down the beam pipe, and that you will never detect, so you will never know what is PL after the collision. Therefore, you cannot even say whether PL has been conserved before and after the collision. It is a question which cannot be addressed experimentally. Alright? But look into the transverse direction. Okay, so this is the z-axis, the beam direction, which is perpendicular to the plane of the blackboard, and this is the plane of the blackboard. Now here there was no initial momentum, because initially there was flow of momentum only down the z-axis. So xy component was not there. Therefore you would say that the total momentum, transverse momentum before and after the collision must be balancing. PTI is the total momentum, that is, you have all the particles which you have detected with transverse momentum, you add their transverse momentum, that gives you the, no, I'm sorry, these should be a multiple, sorry. So these are the vector momentum of the final state. Now if you add them vectorially, if you measure them and add them vectorially, then they must add up to 0, because there was no momentum in the transverse direction to beam width. And this is depicted here by this figure. Now remember, in this definition, for particles with negligible mass, which is the case for all stable standard model particles which you eventually see, electron, quarks which are stable, for particles with negligible mass, Pt is nothing but magnitude of. Therefore, the conservation of Pt and the total Pt is the same thing as conservation of missing energy. This is just one way of putting it. But actually, for the particles like the electron or the muon and jets are streams of hadrons, I will come to it subsequently. But the point is, all their transverse momentum, this in fact is the transverse plane. This circle is in the transverse plane. And we can add their Pt vectorially, and if the vector sum is not 0, then you conclude that some missing energy has been carried out by some particle which did not interact with the detector. And which particle do not interact with the detector? If it is weakly interacting. So the dark matter candidate will generate, I'll come to neutrino of course. So therefore, if a dark matter particle, so this is called, well, here it says missing energy, but strictly speaking, this should be called missing transverse energy or So,
So, sir, what our detector are basically placed along that circle that here you have drawn, right? Because they are at the transverse plane.
actually what is shown here is the transverse plane. Now actually the detector does not cover even the full transverse plane also. I mean, a little bit is
Empty,
left out.
left out.
Little bit is left out. But that I will not focus on at this point. But this is simply, you can look it as the transverse plane. And these particles, this muon, electron or whatever, they are all with their momentum component in the transverse plane. And in the case of no missing transverse momentum, this transverse momentum should vectorially add to
Zero.
0. But if they don't add vectorially to 0, is called a missing ET or missing PT event.
There can be due to Neutrino.
Yeah, sure, I'll come to it immediately. I'll come to it immediately. Now, as he has asked, we have to realize immediately that just as the invariant mass of the two photon does not mean that you have discovered invariant mass P for the two photon invariant mass distribution does not mean that we have discovered the Higgs boson. You have to do a lot of analysis, you have to see that the signal is more than the background and the signal, the difference between the signal and the background events is statistically significant. You have to do everything. However, this is a telltale signal of dark matter production because you have a imbalance in energy in the transverse plane. Now of course we have to do the analysis, and what other people have observed is that nothing happening. It should reduce. Okay. So as many people in the audience pointed out that in any standard model event, no new physics, neutrinos may be produced and neutrinos are exactly interacting. It does not matter whether they are massive or not. So when they are produced in association with other standard model particles, this neutrino will carry missing energy. And the standard model event will show a transverse energy imbalance. Therefore, as soon as you see that there is a missing ET event, you cannot jump into the conclusion that you have seen the dark matter particle. Okay? Now,
Sir, one trivial question.
just 1 second. Just 1 second, I will come back. Yes.
So when they are colliding, okay, you don't have access to the longitudinal momentum because it is inside the beam pipe and you can't observe that. But here when you redefine, because the total energy available is PL and PT both, so you have to know at least
PL I need not know. Why should I know PL? I am just measuring the momentum imbalance in the transverse plane, in the XY plane, perpendicular to the beam, which is covered